Hello, my name is Victor Aarre. I am geophysics advisor with Schlumberger, and today I'm going to talk about spectral decomposition. The title is Understanding Spectral Decomposition. So spectral decomposition involves a lot of elements. So in order to truly understand what it means and how it works, I need to define a few underlying techniques first. So I'm going to talk about correlation and convolution. I will talk about Fourier Transform, and we need to talk about amplitude and phase. We are going to discuss the wavelets you construct, and later we will do wedge modeling. We will look at an important element which is called tuning, and I will discuss the merits of the application, in particular when it comes to vertical resolution. I'm going to show a synthetic data test, and I also present some results on real data. And at the end I will come with some conclusions. So first of all, what is the seismic experiment? The whole assumption around spectral decomposition is that what we call the convolutional model. That means that a seismic trace really is the convolution of a wavelet with a reflectivity series plus some added noise. This is a simplification, but it works really nice in practice. It's fast, simple, and accurate, but it ignores second-order effects like multiples and AVO and transmission loss, etc. We also going to discuss heavily the use, or we are going to use correlation and convolution a lot. You don't really need to look at the equations here. What I want you to understand is that correlation is a measure of similarity. Convolution, on the other hand, it's a filter, meaning that the output is in the same shape as the input. So, and it also means that large and detailed shapes are easier to detect than small or blurry shapes. Fourier transform is really important in these techniques. And as you can see, this equation on the top there, it looks really complicated. A lot of mathematical terms involved, but it doesn't really have to be that difficult. So first of all, we talk about frequency. So that is often used the constant k as an indicator, and the unit for frequency is cycles per unit distance. For time domain data, it is cycles per second, and for depth domain data, it's cycles per kilometer. The output is called the Fourier Transform of the function f, which is in time domain. The Fourier is a complex valued function, meaning that it has a real and imaginary part. But this sounds cryptic, and it doesn't really need to be this difficult. So instead, if we focus on the essentials and we rewrite a bit, it ends up that the Fourier Transform is really just the convolution of your input data with a cosine wave and a sine wave. The imaginary part is coming from the correlation with the sine function. So this means that the real part simply is the correlation between the function f and a cosine. The imaginary part is also simply just the correlation between the function f and a sine function. So there is no imaginary numbers involved, really. When it comes to amplitude and phase, so if you look on the figure here, if the horizontal axis, that's the amount of correlation with the cosine wave, and the vertical axis is the amount of correlation with a sine wave. That constitutes a vector, and then the amplitude is really just the length of that vector, and the phase is the rotation against the horizontal axis. In more detail, looking at, in particular now, the phase, an oscillating wave, it starts at 0 Hertz and it comes to a peak, and that is at 90 Hertz, and then it goes down again and do a zero crossing at 180 degrees. And then it passes down to a trough at 270 degrees, or minus 90 degrees if you like, and it skips up again to 360 degrees. And that has completed a full cycle. But this is an oscillating wave, so that means that it will repeat for a long time, and the phase keeps numbering up. Again, you can either kind of do the wrapped phase, which is in the region 0 to 360 degrees, or you can do the unwrapped phase, which is the full representation without modulation. And this phase is also tied to the recording time, which is in seconds. And here comes a fundamental equation. That means that if you count the number of cycles and multiply by the 360 degrees and divide by the time, then you get the instantaneous frequency, which is a very common term. And finally, on amplitude and phase, we know that because of these equations, we can conclude that pure spectral components with a frequency f, then the instantaneous frequency is identical to the frequency itself. The gradient of the phase over time, meaning the time derivative of phase, is constant, and it is 360 degrees multiplied by the frequency. And it also means that the phase increases linearly with time. Thinking now about Fourier Transform and its properties, what it really means is that if you sum together all cosine functions from 0 to Nyquist frequency, you get a spike. And that is what you see to the right. In the top there, you see the oscillating function along the red dotted line. This is very interesting because this shows you that a spike can be perfectly constructed by the summation of a series of cosine functions. If you see there, this figure is not new. It has been around for a long time, and actually you can see almost the same setup in an old book by Os Yilmaz. What's interesting there is that you see these kind of circling patterns on the plot, and this doesn't look like cosine or sine functions at all. What it really is aliasing. It's poor reconstruction or interpolation for high frequencies. This is for data sampled at 4 milliseconds, and it shows that for frequencies above half of Nyquist, which is 62.5 Hz here, we are starting to get the reconstruction errors, and that is due to a poor interpolator in this case, or a fast interpolator. But if we increase the sample rate to 1 millisecond, this pattern or aliasing completely disappears. This means that in practice, for spectral decomposition, we have to be a bit careful with frequencies above half of Nyquist in our analysis. Going back now to the summation, and then, as we said, a spike is just a sum of infinite cosine functions. But actually, the functions for each frequency, they don't need to be infinite. That's just how it is done in Fourier Transform. But you can also do the same in using what we call Wavelet Transform. In practice, that means that we have a finite number of cycles. But it also assumes that all frequencies have the same amplitude. That is not the case with a regular kind of seismic. You have a kind of central band here is one example. I have muted the lowest frequencies down from 12 Hz and down, and I also muted the high frequencies from 50 Hz and up. And that means that you can see there is in the central plot there are no energy to the right and to the left. And this spike is no longer perfect. Now it starts to look like a wavelet, meaning that you have a central spike and you have side lobes above and below. If we do the same by kind of limiting the number of cycles, you are getting actually almost the same spike back. So this tells us that it is sufficient to only use a few cycles of each frequency in order to properly represent your wavelet. Here we have just even shorter wavelet function or kernel, and if we flop up between these a bit, you can see that they're still very similar, but we are taking a penalty when the wavelet kernel gets too short. And then phase. Here we are looking at the wavelet transform with 0 degrees phase. That means that the peak of the energy is at 0 time, and that you are symmetric around positive and negative time. You can see that on the wavelet to the right, you have the kind of collected all the energy in the middle, and above and below that are identical, wrapped around 0 time. And in this case, I'm using a wavelet with 3 cycles. If we do a phase rotation to 90 degrees, that means that the peak time is coming above 0 time, and you now have anti-symmetry. That means that the bottom is identical but flipped polarity. And you can also see this on the wavelet shape, that the peak comes before 0, and at 0 you have a 0 crossing. We can do the same by rotating minus 90 degrees, and this is what we get, and you see that the result is identical, but it has a flipped sign. This is because there is a 180 degree phase difference between plus 90 degrees and minus 90 degrees, and that means just a change of sign. So now we have understood how we can construct wavelets, or alternatively how we can decompose a wavelet into its separate frequencies. Then we can use this wavelet in order to convolve it with a model. In this case, I have a 2D model here. This is a wedge model, and in this case we have a top layer which is soft. We're coming down to a hard layer, meaning that the acoustic impedance is higher, and the hard layer has a linearly increasing thickness from left to right. On the bottom you have the soft layer. Again, that means that you will have a positive reflector on the top of the wedge, and you have a negative reflector on the base. And the magnitude is the opposite, meaning that the magnitude is the same, but opposite sides. Here is the reflectivity function we get out of this. And what we now want to do is to convolve with wavelets. And here you see how the synthetic seismic response will be if you convolve with a very short wavelet function, which is also band limited. You see it's highlighting pretty nice the points, and what's interesting is that as the layer gets thinner and thinner, the 2 reflectors starts to overlap. That is what we call tuning. And here is just one kind of zooming in on a few locations, and as you can see to the right, the two spikes and side lobes, they are completely separated. But as the layers go thinner and thinner, the seismic response for the 2 reflectors, they will start to interfere and tune with each other for individual frequencies. And at the end, at 0 thickness, it will disappear altogether. Now, let us look a bit more closely on what's going on when it comes to tuning. So here I will show you a small cartoon just to illustrate what will happen when you have a constructive interference situation. On the top you have the reflection for a given frequency for the top of the layer, and that will also have peaks and troughs oscillating. And if you combine this with a seismic response for the base of the layer, you will see that the reflector from the base actually is the same as the reflector for the peak, and these will superimpose, and that gives the combined response like this. This means that we have a constructive interference pattern, and the amplitude will peak at this frequency. Taking the other way, if we change the frequency to double it, then you will see that we still get the wavelet response for the given frequency for the peak, and you do the same for the trough. But when you look at these 2 shapes, you realize that when these 2 are superimposed together, they will cancel out, and the seismic response for that frequency will be 0, a minimum. If we look closer on all frequencies, so here we have from 0 Hz to Nyquist 125 Hz to the right, you see that some frequency responses are strong and they are also dimming out at certain points. So we have peak frequency at 10, 30, 50 and 70 Hz for this layer thickness, which is 50 milliseconds. And the frequencies will cancel out at 20, 40, 60 and 80 Hz. This is a destructive interference in the center, and on the peaks it's constructive interference. And this is the heart of the spectral decomposition kind of method. We want to exploit this, and we will do that by investigating from real seismic which are the peak frequencies and what are the trough frequencies in your data for every time window. And this is called the tuning frequency analysis. What's also important is that we have some ambiguity here. So if we now look at the amplitude plot extracted along the top of the wedge model, you see that you have a certain kind of strong peak, strong high amplitude areas, and you have totally dim areas. And here is one example. 20 millisecond layer will peak at 25 and 75 Hertz. To the 20, 30 and 40 Hertz will peak at 25, 17 and 12 milliseconds. So this is how you can do the mapping from peak frequency to layer thickness. And here is, for those of you who are interested, here is the equation to map between tuning frequency and tuning thickness. But be always a bit cautious, because the thin bed tuning is acting in a particular kind of zone of layer thickness and in a particular zone of frequencies. So you should note that there is a cigar-shaped cone of uncertainty in this setup. That means that you cannot really have a perfect isolation of frequency versus thickness. We can look a bit closer on that by looking at how the frequency resolution varies with vertical resolution. So on the left, we have a fairly short wavelet, which vertical resolution is 100 milliseconds. And if we take this wavelet, which is stationary, meaning the same across all frequencies, and convolve with all possible cosine functions, you get the result to the right. As you can see that the kernel frequency, which is 30 Hertz, will be kept, but we also pass through in the convolution of frequencies above and below. If we now increase the length of your wavelet and correlate or convolve again, then we see that the frequency is narrowing, and increasing again it's even more narrow, but on the expense of the vertical resolution. This has been known for a great number of years, and it even has its own name, and it's called the Gabor limit. And in essence it says that the area is constant, meaning that if you want to have a more precise isolation of individual frequency, then you have to compromise on vertical resolution. So coming to another synthetic study. So here I have constructed a wedge model with a central frequency of 25 Hertz and a 90-degree phase. When I convolve this with the wavelet to the left with the synthetic seismic in the center, you get the output to the right. What's interesting to see there is that we have a peak in the correlation function at 30 Hertz, which fits very well with theory and what we expected. But we also see that we have positive correlations outside this range, so it's not a totally perfect extraction or decomposition. But that is, as I just showed you, it can't be done anyway. We are fighting against physics here. Now, if we should do the same with a Fourier-based method, meaning that you are correlating with both a cosine and a sine function, we can repeat that experiment. And note that in this case, you could say that we are convolving with a complex wavelet. The output you will see to the right there. It is the same general response. You get a peak at 30 Hertz as expected, but you can see that the vertical resolution is somewhat smeared. Now let's move on to a real data example, in this case from the Gulf of Mexico. Here we are looking at a time slice through the seismic amplitude, and as you can see that there is not much really which stands out of geology. A very kind of a common technique in order to enhance this is to calculate RMS in a time window around this slice. And in that case, this is what we get. Now in the red color in the high amplitude areas, you start to see features coming out. And for those of you in the geology area, I hope you can start to see channel features coming out. And this is just out from the RMS amplitude. But we also have a lot of high energy responses from other features in the underground. And if we compare this now with a spectral decomposition, as we do here, then I hope you see that we are now actually able to separate out a lot of the individual geological elements which is captured by that slice. So in this case, I do RGB blending, red, green, blue rendering, where R is 23 Hertz, green is 38 Hertz, and blue is 52 Hertz. And the key point here is that you really see mostly the same as you did on the RMS map, but in this situation you are better able to separate out the individual features. Moving on to another example. In this case, this is from the Barents Sea, and now we are looking at a vertical section only. From the vertical section itself, it's really hard to kind of intuitively see the geology, but by doing spectral decomposition and along a time slice going through that section, you suddenly start to see a delta system. It's a meandering channels all over the section in the center there, bounded by the major faults. And not only that, because we see that the key response is in the blue color, that is the 40 Hertz response, and that means that we can infer that the thickness of this layer is around 12 milliseconds. This is very useful information. So let's go to conclusions. I showed you that tuning happens in nature. Tuning can be exploited, and a fundamental method is the Fourier Transform. It has some good sides, but it also has bad sides. Most often a Wavelet Transform is better, but we will always fight in the trade-off between frequency and time resolution. Thank you very much for watching this presentation. I hope you now have a good appreciation of what spectral decomposition can do for you.